transfer. So heat is transferred from one place or object to another in three different ways. So that is conduction, convection, and radiation. So these are the three ways that we can use to spread heat or transfer heat. So conduction is the process in which heat energy is transferred by adjacent molecular collisions throughout the material medium. However, the medium itself does not move. So how well a solid object conducts heat depends on the bonding within its atomic or molecular structure. So solids composed of atoms that have one or more loose or valence electrons conduct heat and as well electricity satisfactorily. And these are the objects that we call as conductors. So usually, since metals usually have loose valence electrons within their shell, so typically they are also the ones that possess thermal conductivity and electroconductivity. So yun. So usually conduction ang nangyayari when we are talking about transfer of heat between solids and specifically metals. So here are some general observations concerning the conduction of heat. So first, the quantity of heat transferred per unit of time is directly proportional to the temperature difference between the two phases. So let's say we have a phase here and a phase here connected by a slab. Ayan, so this would be our diagram. So second observation, the quantity of heat transferred per unit of time is directly proportional to the area of the slab. And lastly, the quantity of heat transferred per unit of time is inversely proportional to the thickness of the slab. So the value that determines whether a material is a conductor or insulator depends on its thermal conductivity, which is the measurements of its ability to conduct heat, which is defined by the relation K, which is your thermal conductivity, is equals to Q, your quantity of heat, your L, which is your length, and so Q again is your heat and L is your length, T is your time, A is the area, is the cross-sectional area, and the delta T again is your change in temperature. So this is our formula to determine whether an object is a good conductor or a good insulator of heat. So if you are interested naman in insulating your house or keeping certain objects cold when, for example, mag-outing ka and gagamit ka ng isang cooler, and you want to keep your soft drinks or other beverages cold for a sustained amount of time, you are more concerned or you are interested with poor heat conductors, or sa madaling sabi, heat insulators, yung hindi agad nagpapadaloy ng init. So for this reason, the concept of thermal resistance or the R value has been introduced into engineering practice. So R value in a sense is the reciprocal of your K value, which is your thermal conductivity. So R value naman refers to thermal resistance. And kapag mataas ang R value mo, it means your material is a good insulator. Ayan, so it is defined with the formula R equals L over K. So the lower the thermal conductivity, so lower K means higher R value. And higher K value naman implies lower R value. So we can say indeed that your thermal conductivity and your R value are inversely proportional or inversely related to each other. So next we have convection. So convection is a type of energy transfer that occurs when a fluid, such as air or water, comes in contact with an object whose temperature is higher than that of the fluid. So saan ba natin nakikita usually or na-encounter yung convection? So usually, convection is a part of many natural processes. So for example, atmospheric convection plays a fundamental role in determining global climate patterns and daily weather variations. So usually, we observe or we identify convection in natural settings, hindi sa practical or let's say engineering processes. Kasi in these such scenarios, yung mga practical and engineering situations, usually what we observe more often is conduction and radiation. So radiation is the type of heat transfer that occurs without any medium at all. So one of the famous examples of this is the transfer of energy from the sun, in which this energy is transferred to the earth over the empty or nearly empty space. So radiation consists essentially of electromagnetic waves, which led us to say that the radiation from the sun consists of visible light plus many other wavelengths that the eye is not sensitive to, including infrared radiation, which is mainly responsible for heating the earth. So the rate at which an object radiates energy has been found to be proportional to the fourth power of the Kelvin temperature and to the area A of the emitting object. So the rate at which the energy leaves the object is defined in the formula below. So we can see here, R is equals to E sigma T raised to the fourth, where E is your emissivity, which is a number between 0 to 1 that is characteristic of the surface of the radiating material. So for example, very black surfaces such as charcoal have emissivity values closer to 1. So emissivity can be represented by either E or the Greek letter epsilon. So going back, very black surfaces has emissivity close to 1, whereas shiny metal surfaces have close to 0 value of emissivity, which means that shiny metal surfaces correspondingly emit less radiation. So for the second variable in our formula, the sigma represents the Stefan-Boltzmann constant, which has the value of 5.67 times 10 raised to the negative 8 watt per square meter Kelvin to the fourth. Ayan, so this is the value of this Stefan-Boltzmann constant. So in CGS units, we can refer to its unit as ergs. So simply speaking, the Stefan-Boltzmann constant can be also said as 5.67 times 10 raised to the negative 8 ergs. So yun. So the whole equation is the formal statement of the Stefan-Boltzmann law, which is just about the rate of radiation of a certain body. So another formula that we can that is usually used in radiation is the Prevost law of heat exchange. So the Prevost law of heat exchange states that a body at the same temperature as its surroundings radiates and absorbs heat at the same rates. So yon.
A cylindrical copper rod of length 1.2 meters and cross-sectional area 4.8 square centimeters is insulated along its side. The ends are held at a temperature difference of 100 degrees Celsius by having one end in a water-ice mixture and the other in a mixture of boiling water and steam. At what rate is energy conducted by the rod and does the ice melt? For the rate energy conducted by the rod, you use the heat transfer formula Q over T equals permittivity times area times change in the temperature or the temperature difference over length. That is equal to 385 watts per meter Kelvin. That is the permittivity of the copper rod. Multiply its area. The area is in square centimeters, so you convert it into square meters. For the change in the temperature is 100 degrees Celsius. Since it is the difference, it is also the same in Kelvin. Over the length, that is 1.2 meters, equals 15.4 joule per second. For the rate the ice melt, you use the ratio of the energy conducted by the rod, 15.4 joules per second, over the latent heat of fusion of ice. Since ice is the solid form of water that is that has a latent heat of fusion of 334 joule per gram. And if you divide, that is equal to 0.046 grams per second. A solid cylinder of radius R1 equals 2.5 centimeters, length H1 equals 5 centimeters, emissivity of 0.85 and temperature of 30 degrees Celsius is suspended in an environment of temperature 50 degrees Celsius. What is the cylinder's net thermal radiation transfer rate P1? If the cylinder is stretched until its radius is R2 equals 0.5 centimeters, its net thermal radiation transfer rate becomes P2. What is the ratio of P2 over P1? In this problem, we first find the initial area of the cylinder. So, if you recall in your geometry, the surface area of a cylinder is equal to 2 pi r squared plus 2 pi rh. So in this case, we are dealing with the initial area of the cylinder, meaning it is not yet transferred by heat or undergo heat exchanges. So we have R1 equals 2.5 centimeters, and if you convert that to meters, that is equal to 0.025 meters. And for h, we have 5 centimeters, the height, that is equal to 0.05 meters. And if you substitute that in the area is equal to 0.012 square meters. And for the radiation, we have the Prebus law of heat exchange, that is equal to A sigma area multiplied by the change in temperature. In this case, the environmental temperature raised to 4 minus the temperature raised to 4. So in the problem, we have given an emissivity, that is E, of 0.85, and sigma here is the Stefan-Boltzmann constant, that is equal to 5.67 times 10 raised to negative 8 watts per square meter Kelvin to the fourth. So the area is 0.012 square meters, while the environmental temperature is equal to 50 degrees Celsius. Then you add to 273, that is equal to 323 Kelvin. And for the temperature, it is equal to 30 degrees plus 273 equals 303 Kelvin. And you raise that to 4 for both temperatures and find their difference. And if you calculate that, the radiation is equal to 1.42 joules per second or 1.42 watts. For the second question, we are asked to find the rate of radiation at which the cylinder is stretched to a radius of 0.5 centimeters. So as you recall, the stretched cylinder and the first cylinder have equal volumes but different surface areas. So we are only given the radius of the second cylinder or the stretched cylinder, and we need to look first for its height in order to determine its surface area. So for the surface area, in order for you to compute it, you need the height. As you recall in the previous slide, we used the formula 2 pi r squared plus 2 pi rh. So for the second height, that is equal to h1 multiplied by r1 squared over r2 squared. So it is from the equal volumes of the cylinder, and if you derive it, you cancel the pi, and h2 is equal to h1 R1 squared over R2 squared. So if you plug in the values, you will obtain 1.25 meters. So that is the height of the second cylinder. So which is different from the height, which is only 0.05 meters. So next, we find the surface area of a cylinder of the stretch cylinder that is equal to 0.039 square meters. So again, you will use the Preble's law of heat exchange. In this time, you will just change the area to 0.039 square meters, and that is equal to 4.62 watts. And for the ratio, that is equal to P2 over P1. So 4.62 watts over 1.42 watts equals 3.25. So that is the ratio of the cylinder in terms of its rate of radiation from P2 and P1.
Thank you for listening. I hope you learned something today and see you on the next discussion video.